Back to the class of differential equations and the matrices. Guess what? Somewhat we reached to the conclusion of this section 3.6. It's about the basis and the dimension. Okay, we consider this set as the basis of vector space if the set is linearly independent and the span of the set turns out to be the entire vector space. And hopefully it's easy to understand the vector space. Actually, this one forms the basis for the vector space of R3. And it has three vectors. That's the dimension, that's the dimension, that's the dimension. Okay. And one more example I'm talking about here is this class, it is of differential equations and the matrices. And whenever if it's all possible, trying to put those two topics together. Okay, certainly we know vectors, vector spaces, and now we know dimensions and the bases. And indeed, what I want to say here is I hope you remember, we mentioned this earlier. So the solution of certain kind of differential equations indeed is a vector space. It is a vector space. And specifically, the first order solution of a first order linear homogeneous differential equation, it is a vector space of dimension 1. First order, dimension 1. And then we have the conclusion similarly for the second order. It's a vector space of dimension 2. And certainly, I think in our next chapter, we will work more on second order linear differential equations. And certainly, homogeneous second order linear differential equations is included. But anyway, for this moment, I just want to take a quick look. Actually, we do have another case to cover. We solve system, and many times you see a system may have many solutions, right? How do we identify the situation when we have a system with many solutions? And usually, the system we consider it is the so-called homogeneous system. If the right hand side it is 0, and then that is a homogeneous system. Ax equals b using the matrix fashion. Okay. So in this case, I hope you see clearly simply looking at two equations, right? Looking at the system, there are two equations. But anyway, there are 4 variables. So indeed, I hope it's easier to tell there are infinite number of solutions. And also, all those solutions, they are the set of solutions turns out to be a vector space. It turns out to be a subspace of vector space of R2. And so we want to identify the basis and the dimension of the solution. Okay, basis and the dimension of the solution. So here is what I did. I hope you still remember those elementary row operations, right? Elementary row operations, and also remember the RREF, reduced row echelon form. So what I did, I just copied down the coefficients from system. There are 2 equations, so there are 2 rows. And also because it's homogeneous, which means the right hand side, entire right hand side is 0. So I really don't need to bother with those zeros because we are using elementary row operations. The right hand side is all 0. It doesn't matter which operation you use, and the right hand side stays at 0. And then I understand that to solve system, usually it is easier to get the coefficient into the reduced row echelon form. And I take this as one as a pivot. And then remember in the pivot, in the column where the pivot is, it is the only 0 in the column. So I'm going to make this one as 0. What I did here is row 1 multiplied by -1 add to row 2. So in the pivot column, it is the only non-zero element, and usually we make the pivot as 1. Okay. And then what we want to achieve here is actually after doing the first round of manipulation, I think I got another very nice result. The 3 it is converted into 1 already, right? So this should be considered the next pivot. And it is further to the right compared to the first one, right? And then also we want to make sure in the column where the pivot is, other elements got to be 0. So this is what I did. Row 2 multiplied by -1, add the result to row 1. And then, well, let's say assuming everything's fine, then how do we still identify the solution? Well, if you have harder time to see from the matrix, from the reduced row echelon form, how about to convert this RREF, reduced row echelon form, back to a system? So which simply means x1 can be written as x3 and x4. x2 also can be written as x3 and x4. And I think I don't need this 0 here anymore. And x3, x4 are 2 free variables. And how about let's put it in a more formal way. I consider x1, x2, x3, x4. That's a 4-dimensional vector, right? That's a 4-dimensional vector. So I have x1, x2, x3, x4 there. Okay. x1 is such like we just did. x2 is such. And x3, x4, they are free variables. And also what I did in the next part, I tried to separate the notation R and S. Okay, notation with R only, notation with S only. And so it turned out to be those 2 factors, 5R, -2R, R, and 0, right? There's no R from this single S. But anyway, you can consider this a 0 times R. Then I factor R from the first column vector here, R times this vector. And also we do have the second column vector, and also I factor out this S from the second column vector. And seeing this arrangement, would it make sense to you? I'm seeing x1, x2, x3, x4 as a linear combination of those 2 factors. Okay, the column without R and S, because R and S are just the scalar quantities. So I say the solution, it is a linear combination of those factors. And also I hope you see those 2 factors are linearly independent. For 2 factors, okay, yeah, they are linearly dependent if and only if they are scalar multiples of each other. So clearly I'm saying those 2 factors, they are not scalar multiples of each other. So they are linearly independent. And the set we are looking for here, the solution space, it is the span of those 2 linearly independent vectors. So indeed, as it is the solution space, and there are 2 factors, this forms the basis. There are 2 factors in the basis. So the dimension of the solution space, it is 2. I think this concludes the discussion of section 3.6, basis and dimension. Thank you for watching.